For today's lecture, we will be looking at different topics. The first one is the translinear principle, what this means and why is it useful. We will look at resistive networks and current mode resistive networks. Then I'll describe a basic building block that is actually very useful in dealing with current mode circuits, which is called the current conveyor. It's equivalent to the op-amp in voltage mode circuits. And we'll look at two examples, two classic examples of current mode circuits, the Gilbert normalizer from Barry Gilbert and the winner-take-all network. And the lab will be on the winner-take-all network, but you'll see that the winner-take-all network basically has all of these things inside, so you'll be testing all the circuits. The translinear principle, let's start. Oh, sorry, first let me just tell you, current mode design in the history of electronics is relatively new. I mean, it goes back maybe 30 years, but or 20, but compared to voltage mode circuit design, it's much more recent. So historically, analog design has been viewed as a voltage-dominated form of signal processing, meaning that the input signals and the output signals are voltages, and most of the time the parameters are also voltages, like the bias voltage. However, with the advent of bi-CMOS first and now CMOS technology and shrinking of feature size, reduction of power supply voltage, the current mode circuits started to become more and more popular. So when voltage supplies were 20 volts or more, there was no problem in range of using voltages to represent signals, and in processing voltages, adding them, subtracting them, multiplying them. But you know, from the technology progress, shrinking feature size has led to decreasing power supply. So for example, when I was designing my first chips in the mid-90s, just to give you an idea, the power supply was 5 volts. Then after some years, it went down to 3.3 volts. After some years, it went to 2.4, then 1.8, 1.1. And now we are at power supply voltages of, you know, even 0.7. Some at state-of-the-art circuits are even, you know, a few hundred millivolts. So you can imagine that with such a small power supply, that's the sort of 0 is the minimum, the VDD is the maximum. And with such a small range, it's more and more difficult to implement analog circuits that can actually work reliably. And so that's why already when power supply voltages were around 3.3 and 1.8, current mode circuits started to become more popular. And here are some some books that are representative. Chris Tomaso is one of the most important figures in the world of current mode design. But there's also many famous researchers and industry leaders that actually have proposed different current mode circuits. And these current mode circuits, you'll see, as I mentioned, we will look at the translinear principle and translinear circuits and the current conveyor. There are some other that we will not touch upon in this lecture, which are dynamic current mirrors, switched current integrators, and current feedback amplifiers. These are described in these textbooks, but you should at least be aware there is a wide range of circuits that are using currents as input and output as the signals that they process, which are becoming more and more popular, both in academia and industry. So if we go to the translinear principle, this is basically a principle that was, as I said, coined by Barry Gilbert in 1975. It's using circuits that have a transconductance that is linearly proportional to the output current. You already know what the transconductance is. For example, in the transconductance amplifier, usually you use the term conductance, which is 1 over the resistance, to indicate a device that has 2 terminals and in which the voltage is applied on the 2 terminals, and you measure the current flowing through the 2 terminals, like a resistor. A transconductance is a device in which you have 2 terminals that you use to apply the voltage, And then there is a third terminal that you use to read out the current, like the transconductance amplifier, the transamp. And so translinear circuits have a transconductance that is linear, in which translinear circuits have a transconductance that is linear with the output current. So for example, in the transconductance amplifier, if you use voltage inputs which are relatively small, and you're in the linear region of the hyperbolic tangent, you could use that as a translinear circuit in that particular region. The same for the diff pair, the differential pair. If you use it in the region in which the current is linear with the input, then you could think of that as a translinear circuit. Of course, as soon as you go above these few millivolts in which everything is linear, then this doesn't apply anymore. So in BiCMOS technology, where there were bipolar transistors, or even with monolithic bipolar transistors, it was easy to implement these types of circuits because bipolars have a transfer function that is an exponential. The output current is the exponential of the voltage. In CMOS, using MOSFETs, this is true, as you know well now, only in subthreshold. So if we use the MOSFET in subthreshold and in saturation, we have this exponential relationship. It's because of this property of the exponential. But we have to be in subthreshold, and then we get this very nice property that you will see can actually be used to simplify the analysis of the subthreshold circuits, or to help you in designing invent new circuits. Now, the translinear principle is based on the use of translinear circuit elements. So in this case, I'm showing you a picture from Barry Gilbert's book with bipolar symbols, but you could replace all of these bipolar transistors with MOSFETs, assuming they are operated in subthreshold. And the principle defined by Barry Gilbert is written here. So in a closed loop containing an even number of forward bias junctions, so forward bias transistors, arranged so that there is an equal number of clockwise facing and anti-clockwise facing polarities, the product of the currents in the clockwise direction is equal to the product of the currents in the counterclockwise direction. So this is a complicated definition, but you'll see it becomes really simple when we look at circuits. I'll explain it to you in simpler terms. But essentially, when you have a circuit and you have, let's say, clockwise, so if you go from VGS from bottom to up, let's say from the source to the gate for a certain number of elements, and then you have the VGS going from the gate to the source in another set of elements, the product of the currents of the bottom to up is equal to the product of the currents of the top to down. I realize this is not any clearer than the other definition, but maybe if we go through the circuits, it's going to become clear. And as I said, just interrupt me at any time when we go through these slides. The definition translates into a formula. So basically, it's saying that if you have a loop or a circle in which the sum of the voltages that determine the translinear element. So in our case, if we have MOSFETs, the gate to source voltage, the sum of these VGSs is equal to 0, then the product of the currents flowing through them is equal to 1. Now, if we go back to this equation here, you can see it. If the sum of the VGSs, or even just one VGS, is equal to 0, the output current is equal to, the exponential becomes 1. So the output current is just equal to I0. So that's just property of the exponential. If on the exponent you have a sum of voltages and the sum adds up to 0, then you can break up the sum into products of individual, e to the VG1 times e to the VGS1 times e to the VGS2 times e to the VGS3. So it's just the property of the exponential, which becomes the product of all of these individual currents is going to be equal to IDS over I0. So this is basically what this formula is saying here. If these are VGSs, you can write and you have MOSFETs, basically that is equal to the log of the ratio. And the sum is equal to 0, the product is equal to 1. Now let's finally go to some, we will see the circuits when we look at the current conveyor. So this is just to give you the definition and to help you understand that what we need to do whenever we analyze these circuits is we need to check all of the sum of the VGSs. If we find a loop where we have the sum is equal to 0, then we can really simplify the analysis by using this principle. Again, I realize it's confusing now. It'll become clear when we look at circuits. But before looking at circuits here, now there is another building block that I would like to introduce, which is the one of current diffusers, which are used to implement models of resistive networks. And so why are we either bothering with resistive networks? Resistive networks are actually very useful. If you see networks of this type, these were being used in the 70s when they were doing analog computers. This is a very simple one. It's the simplest you can think of. But you can see what happens if you inject current, and if these currents represent signals, for example, coming from photodiodes or coming from some other instrument, if you inject all of these currents into a network which has laterally coupled resistors and then vertical resistors, the effect of that will be to diffuse the currents laterally. And if you think of the diffusion, implementing a diffusion equation in physical devices is actually very useful. Of course, now everything is being done with MATLAB by simulating, integrating differential equations in numerical methods. But in the 70s, there were many examples of full custom ASICs that were built to solve different types of equations. And the diffusion equation is one of the most common ones. Diffusion equation is used to model the diffusion of heat in materials, the way that materials bend. Any finite element that uses diffusion is useful. And if you can have a chip or even a circuit with discrete building blocks that can actually solve this equation through the physics of the devices in real time, then it can be very useful. So this is why in the 70s, these types of networks were being used a lot. You can even think of these coming from photoreceptors, for example. And if you want to do smoothing of an image, if you know about, in computer vision, you use smoothing filters. This could be doing the smoothing. If these are all pixels of an image, the voltages at the nodes here would represent the smoothed version of the image here. And of course, now we don't want to just go in the shop and buy a bunch of resistors and have a huge network that is larger than what we could put on a table. We can actually integrate all of these devices in VLSI and have very compact diffuser networks. The problem is that in VLSI, it's very hard to build resistors of desired conductances, meaning that they either occupy a lot of space, you have to have long poly wires, or once you design them, you cannot change the conductance values, or you have to use wells. So it's very complicated. So the best way to do it is to try to use the linear or the ohmic region of a MOSFET, and then to use MOSFETs to make these resistive networks. So MOSFETs, they can work in subthreshold, above threshold, ohmic region, and saturation region. So if you use the MOSFETs in the ohmic region, so in the whether it's subthreshold or above threshold, it doesn't matter. But if they're in the ohmic region, then you can replace those symbols with the equivalent resistance, the conductance, and then you can implement these networks. And of course, in order to use these as diffusers, as resistive networks, you have to apply input currents. That's why it comes in this current mode lecture, because the input signals are currents. The output signals could be the voltages on the nodes, or it could be the currents going through the resistors to ground. So in this case, the input is a current. The output could either be a voltage or a current, but it's still a current mode circuit. Now, how do we implement, resistors? As I said, we need to use them in the ohmic region. The ohmic region is the one in which the feed-forward current is comparable to the reverse current, when the drain, and the source voltages are similar. Remember, the full equation of a subthreshold MOSFET is ID is equal to I0. Maybe I wonder if I can draw here, annotate. So if you can see my annotations, it looks like you can. Oh, but then it goes away. Okay, so this is the full equation. I forgot to divide by UT, but if you divide everything by UT, or if you normalize the voltages with UT,
we can't see the equation.
Oh, you can't? On the top right? I guess it went away. I see it on my screen, but I guess I'm the only one seeing it. So let me just tell it to you. It's IDS is equal to I0 e to the kappa Vg minus Vs divided by UT. That's the standard one, like the one that we have down here, times 1 minus e to the minus VDS over UT. That's the full equation. And then we say if VDS is greater than 4 UT, the e to the minus VDS over UT becomes e to the minus 4. E to the minus 4 is basically negligible compared to 1. And so we are left with the simple equation in saturation. On the other hand, if VDS is not greater than 4 UT, if VDS is small, then you cannot neglect that. And the full equation, then if you just multiply all the terms, the full equation becomes the one that is shown down here on the bottom right. Yeah, you can see my mouse, right? I assume you can, because I can see it on the other screen as well. So if you rewrite it in these terms, you can see that it's basically taking a forward component of the current minus a reverse component of the current, the forward and the reverse. So if we are in subthreshold and if we are in the ohmic region, basically we are dealing with the diffusion of minority carriers. Sorry, in this case, it's majority carriers going in both directions. And by making small different voltages in either the source or the drain, we can increase linearly the reverse or the forward component. And so that's why it's called ohmic, because then there is a linear relationship between the net flow of the current, which is the difference of the two, and the difference between the drain and the source, giving a fixed gate voltage. So then actually Eric Vito, who is Swiss in Lausanne at CSEM in Neuchâtel, actually not really Lausanne, noticed this already in the late 80s and pointed out if we define a pseudo voltage as just by definition is something which is a V0 e to the minus V over UT, then we can define the pseudo conductance, which is using the same trick, which is I0 over V0, which will be the conductance times this exponential. And you can write this equation as a linear equation in which the conductance is is multiplying the differential voltage. So this current is linear with the conductance, with the pseudo conductance and the pseudo voltage. So that's why these subthreshold transistors in the ohmic region are translinear elements, because if you write it as a pseudo voltage and as a pseudo conductance, you can immediately see that there's a linear relationship between the current and the voltage. Again, these are all just definitions, but you'll see that when we get to the circuits, these come in handy. It just simplifies the analysis. It doesn't change anything in what we've seen up to now. It's just pointing out these observations that if you're in these regions, everything is linear with a small differential voltage, and you can then implement resistive networks with these transistors. And this is what actually, let me tell you, when Eric Vito in Switzerland in the late 80s was realizing this was actually, just as a anecdote for you to know, this was actually what saved the Swiss watch industry, because in those years, Japan was coming out with very low power watches, Casio and all sorts of these digital watches with batteries that would last for months and months. And the Swiss watch industry was in a crisis because of the power consumption, and Eric Vito decided to use transistors in subthreshold to minimize power consumption. And because there was this push from industry, in this case the watch industry, to innovate, Eric Vito found out about this subthreshold, that you could actually use this subthreshold region of operation, which up to then was completely ignored because everyone was doing only above threshold, and then managed to save the watch industry by helping the Swiss watch industry produce things that were also very low power. At the same time, these are the years in which at Caltech, Carver Mead was getting inspiration from biology, from a biologist, actually, Misha Mahoad, to model neural circuits using subthreshold transistors because of the diffusion. Because in neural circuits, ions flow through protein channels because of diffusion. If we can use electrons to flow through transistor channels because of diffusions, we can make very elaborate and faithful models. So in these two parts of the world, independently, in one case pushed from industry means, in the other case pushed from just academia, basic research, they came up to realize that you could use transistors in the subthreshold domain to do computation. And both Eric Vito in Switzerland and Kwabena Boahen in Carver Mead's group at Caltech proposed such a circuit, which is called the current divider, to implement resistive networks. And so here it's again a very, very simple circuit. Nothing changes. You could analyze it using all of the things you learned so far. But if you use either the pseudoconductance trick or if you use just the translinear element, it will be easier to figure out what's going on. And this is a current divider circuit. Basically, it's everything, as I told you, is using currents as input and output signals. All of the voltages are fixed. You don't change the voltages. And then you see what happens if you have an input current on one side and an input current on the other side. You want to see what is the output current on the two sides as a function of the various parameters, which are these fixed voltages, V1, V2, and V3. And so basically I just won't go through the analysis, but it's really easy to do. You assume everything is in subthreshold. You cannot assume that they are in saturation. You have to use the full equation, which is this one here. You have to use the drain, the source, and the gate voltage, not only the gate to source voltage. And then you can figure out what's going on by putting together all the equations. You use Kirchhoff's law, you use the equation for M1, M2, and M3, and you end up finding out, if you trust me, that the current going through M3 depends, of course, on the gate voltage of M3, on this V3, but it also depends on what's happening on the two sides, on I1 and I2, and it's actually linear with the difference of I2 minus I1. So if you write all of this together and you collect all of the terms, you can then see that the current flowing through I3 depends on V3 minus V2 or V3 minus V1. And if V1 and V2 are the same and we just call them Vref, it's V3 minus Vref times the difference of the two currents. And this exponential, this is constant, right? V3 is constant and the ref is constant. So this is basically, this is called the diffusion factor, or the space constant. Then the current from the transistor is linear with the two currents. And depending on which one is bigger, it will be going one way or the other. So this is basically saying that we have a resistive element which has a space constant factor that allows the current to flow linearly in one direction or the other. Now this, as it is alone, it doesn't really, it's nothing surprising, but if you remember the resistor network I had with the discrete components at the beginning, and you put many of these together, you will see that it's exactly the same. So now if our input currents, in this case, the input currents come from the bottom, come, for example, from photodiodes, and we look at what happens at the output currents will be something that depends on the difference of the currents. And so the difference is like computing a gradient. So, and the smoothing function is the integral. So it's looking at this difference. So in this case, if the currents come from photodiodes, the upper currents will be the smooth version of the input currents, and you can have a smoothing function in current mode. And this is going one step further. If you connect all of them together, it's showing you now that you can actually implement the diffusion equation. I told you the diffusion equation actually is very useful for calculating finite difference elements, for calculating how heat transfer, and in many other physical processes. And what's shown up here is the diffusion equation in voltage mode. And what's shown here is putting together the current diffuser with multiple nodes, and then just writing, what is the output current depending on the input current if you have more than just two, if you have n nodes. And again, if you just go back to this formula and you iterate it from, I1, I2, I3, all the way to ij, and ij minus 1 and ij plus 1, again, if you trust me, you will come up using this iterative procedure with a closed form equation, which is written down here, which tells you that the output current of one node depends on the output current on the left and the right nodes in this way. So that you have a space constant that is multiplying, I out j plus 1 minus 2 I out j plus I out j plus minus 1, and it's equal to the I out j minus I in j. So it's nice because you only need to know, in order to understand what is the output, you only need to know what is the input and what's happening to the left and to the right. And if you think of if you see this, this is the discrete version. If you think in continuous form, this is the discrete version of the diffusion equation. You have a second order derivative on the left side and the difference on the right side. So it's exactly the same here. And again, you can write this e to the kappa over ut vg minus vr as a lambda. And if you actually have e to the kappa over 2 ut, you can even write this as lambda square, which is exactly the same term of the diffusion equation. Which basically tells you, if I change the difference between these parameters, VR and VG, I change how much current flows laterally or how much current flows vertically. So if I want to smooth a lot, I have to open up the lateral connections. So VG has to go up. So my space constant goes up and I smooth a lot. If I don't want to smooth at all, I put VG to 0, and then the output is just equal to the input. And then by changing VR, you have an extra knob. So VG minus VR is really what counts. The difference in these two conductances, if you want, if these are used in ohmic region in subthreshold, is really what counts. So that's how basically to implement diffuser networks or resistive networks. And as I said, the most simple way to use it is to apply photodiode currents. So you could have a smooth version here, but we will see that we can actually apply it also in other cases. For example, with the winner-take-all network, to smooth input signals to the winner take all. This is the equivalent version of the circuit with resistors. And if you just write it and you use Ohm's law with these G and R, you obtain exactly the same equation. In this case, the lambda constant is 1 over square root of Rg, the space constant. But again, it's just doing algebra. If you do the algebra on writing down Kirchhoff's current law and Ohm's law, and then doing this iterative process, you can come to the closed form solution again, and you get exactly the same equation. This is just to show you that if we do use MOSFETs in subthreshold, in the ohmic region, we can really emulate, not even approximate, directly emulate these resistive networks that were actually very popular in the 70s. But in this case, we can integrate many of these. This is, it could be like a few nanometers long, or hundreds of nanometers long in a CMOS chip. And we can really have thousands or millions of these on a chip. If we have to do a very large diffusive network, we can really integrate many and many of these on a single chip. Okay, so are there any questions on these diffuser networks? This, I realize I went pretty quickly, but it's just to give you some background on what was being done before, what can be done now with CMOS, and also that it was actually found independently at the same time, both in Switzerland and in the US at Caltech, by Quabena and Covermead, of course, and by Eric Vito and his students. Actually, keeping this idea of giving you more background information, one of the students that was with Eric Vito at the time, that was actually getting his PhD at EPFL, was Andre van Schaik. Andre van Schaik now is at the University of Western Sydney, and we have a tight collaboration with him. So he was actually a student of Eric Vito when Eric Vito was finding these or inventing these circuits. And he's also now involved in chip design and in neuromorphic. He's actually the director of the International Institute of Neuromorphic Engineering in Western Sydney. So there is still a very close collaboration between Andre van Schaik, Quabena Wine, us in Zurich, and the community in general. Okay, so if there are no questions on the current mode resistive networks, we can go on to this other building block, which was also sort of invented in the 70s, and it's still being actively used today, which is the current conveyor. And I told you at the beginning, the current conveyor is like the op-amp in current mode circuits. So when people were starting to realize that there were problems with the voltage reduced voltage supplies and limited dynamic range in voltage mode, and we're trying to invent new ways of doing computation using currents, they thought really we need something like an op-amp. So the invention of the current conveyor came from top down, from the need of having a building block and from definitions. So the definition of the current conveyor, first people invented the definition of the current conveyor, and then people invented the schematics that actually, comply with the definition. So the definition is basically saying that, if we want to do current mode computation, we need a building block in which currents are conveyed from the input terminal to the output terminal. So the input could be X or Y, and the output is Z, while decoupling the circuits. If you think of the op-amp, that's what the op-amp is doing, right? You get V1 and V2 at the input terminals of the operational amplifier, and V out is at the other end. And the input impedance to the operational amplifier is infinite. So you completely decouple the input from the output. And people were saying, if we need an op-amp for currents, we need the same. We need something that takes an input current, conveys it to the output, and decouples the circuits connected to these terminals. And we want to use this building block to do, computation, to add, subtract, amplify, filter, and all of these things. And I told you this was the 70s. Actually, it was even before. It was the late 60s. This definition came from Smith and Cedra in 1968. And so the full-blown definition, the formal definition, has actually these 3 bullet points. The potential at the output terminal is independent of the current applied at the node Y. So like the op-amp, you could have either one terminal or the other terminal could be the input. So X or Y could be the input. An input current that is forced into node X results in an equal amount of current flowing into node Y. So this was an additional definition that is actually useful, you will see later, for computation. And then finally, the input current flowing into node X is conveyed to node Z, which has the characteristic of a high output impedance current source. This is to comply with the idea that we want to decouple the circuits. So again, to summarize, if you look at the output terminal, what's happening on the output terminal in terms of the voltage is completely independent of what's happening at the input. If you apply an input current on one of the 2 terminals on X, then the same thing will happen on the other terminal, the node Y. And then if you look at the output current on the output node Z, is independent or is decoupled, sorry, from the input terminal X. And this here, you see a schematic diagram that is actually satisfying these 3 equations. The input terminals are X and Y. The output terminal is Z. If you apply an input current on the Y terminal, it results in the same input current flowing through Y results in flowing through X. It's because of the current mirror. And then this current mirror is copied again. So whatever current is flowing through Y is conveyed to Z. So the output current Z is equal to the input. In this case, it's just a 1-to-1. So the current conveyor is just conveying the input current into the output terminal. But this circuit here, basically, if you read these 3 statements, this circuit is satisfying all these 3 claims. So this is one example of a current conveyor. There are several examples. This is not the only one, but this is one example that really allows you to take some input currents, bring them outside, and then decouple the circuits that are providing these input currents on one side from the circuits that are using this current or consuming this current on the output side. Yeah, so this is just, yes, here's a question is why, in this case, why, you can, in this case, you can change the names of the terminals. In this case, Y is being copied into X. The input is IY, and IX results into being a copy of IY. So here the 2 terminals X or Y are, you can swap them. So the statement here should be to satisfy with the circuit is an input current that is forced into node Y results into an equal amount of current flowing into node X. Otherwise, we should just change these names, and this 0.2 would be correct. But yes, this is an imprecision in this circuit schematic. The two nodes should be changed, or you just swap X and Y. That's the idea of the current conveyor, that X and Y can also be swapped. Okay, so now let's, as I said, there's not many, but there's several circuits that can satisfy the current conveyor. Some actually will satisfy maybe not all 3 points, only 2 of the 3 points, but they are still considered as current conveyors in the literature. And we can go on to seeing what actually we will use in our circuits. And this is the current conveyor that is very commonly used in the rest of the circuits that we will see. And you can see here what's going on. We force a current into node Vy. This is being copied into node Vz. Sorry, it's being copied into node Vx, sorry, and the current in the output terminal Vz is decoupled from the current in the input terminal Vy. And as I said, this building block is used in many current mode circuits. So current mode low-pass filters, current mode multiplier circuits, current mode winner-take-all circuits, and so on and so forth. Now, if you want to see really what happens, it's a pain. I cannot draw on the schematics. I see it on my screen, but it does disappear on the other screen. It's really a pain. maybe when we go to more complex circuits, I just share just a white screen and I just redraw them. But here, this is just the definition, so it's not worth it. It's just to tell you, if you apply an input current, that will set, let's actually go through it. If you apply an input current, this current will flow through M3. You know, in subthreshold, the gate of M3 will be the log of the input current. Remember, if we set a gate voltage, the current is exponential with the gate voltage. I is equal to e to the kappa VGS. If on the other hand we force an input current, the gate will just go to the log of the current. So it's the same. Sorry. So the Vx is the log of Iy. Vx is this node here. Now, if we have an output current, sorry, if we have a current Ix, which we can set to be equal to Iy or to a proportionality factor, that will force the current to go through M5, which will then force the gate of M5 minus Vx, VGS, remember the Vg minus Vs to be the log of Ix. And then that will result in Iz. So Iz will be equal to Ix. Vx will be the log of Iy. This is basically the two properties of the circuit. And because of these two properties, it's considered a current conveyor. But again, this sort of an abstract building block, it doesn't really make sense. It'll be much more clear when we actually use it in different circuits, like the low pass filter, the multiplier circuit. So let me go to the multiplier circuit. So this one, I think it does make sense for me to draw it so we can go through it easily. And let me see if I can share the screen here so I can this will stop other people sharing. So I'm drawing the current conveyor that you saw before. This is the current conveyor, if you remember. We have an input current here, Iy, and we force an X current here, Ix. So this is exactly the same building block that you saw before. This is the current conveyor. Now I just extend it. I just draw another. So I basically copy this voltage here. And I have another current, which I called IW. And I take this and I use this as the output current. Okay, now all of the things we discussed about today will start to come together. So let's look at the VGSs. And if you remember the translinear loop, whenever the sum of the VGSs is equal to 0, the product of the currents is equal to 1, just because of the properties of the exponential. I hope this is still clear in your mind. And I'll go through the various, this one VGS plus this VGS minus this VGS minus this VGS is equal to 0. Do you see that? I start from ground, I go up, and I go back to ground. I hope that's clear to everyone. I mean, we can write it. It's the first VGS is, let's just give them some name. This is Vx, this is Vy, and this is Vw. And this is Vz. So the first VGS is Vx. Vx. The second VGS is Vy minus Vx. Then the third VGS is Vw minus Vy. That is going down, so we have to say minus. Sorry, it's plus. It's going down, but I'm still following the same, so it's a plus. Plus Vw minus Vy, and then plus ground minus Vw. so if I follow the arrows, I'm just following the arrows, and so the the third VGS is actually is minus VGS, and the other one is minus VGS. So this would be VGS 1 plus VGS2 minus I don't know how to call them, GS3 minus VGS4 is equal to 0. Is this clear to everyone? Silence. Hello?
Yes.
Ah, thanks, Sham. I thought I had dropped. Okay. So now let's, if you remember the translinear principle, it's saying that if you have a sum of voltages equal to 0, the product of the currents is equal to 1. So let's write these currents. So the current through the first VGS is the first transistor. Can you actually see the pointer going around the first transistor, moving around?
Not really.
So
We see what you draw.
Okay, so I'm drawing this arrow here. This is the first current. This first current has to be equal to IY. There is nowhere else for IY to go. So the current flowing through this first transistor is IY. So for this one, I write IY. The second current is the VGS of the second transistor is this one. I mean, the second transistor that we look is the one that I just drew now. And the current flowing through that one is IX. There's nowhere else for the current to go. So that would be times IX. Finally, there is the current flowing through the W transistor, this one here. And that one is minus VGS. So if we have, the exponential, if the exponential has the minus term, the current is, instead of multiplying, is dividing. Or it's just to keep it nice in the drawing, I'll just say times IW to the minus 1. It's like I'm dividing by IW. And finally, the last current flowing through the transistor is just by definition is IZ. And also that one has a minus VGS, this here. So it's IZ to the minus 1. Now, so what is IZ? IZ is equal to, so all of that is equal to 1, remember, the product is equal to 1. So if I want to know what IZ is equal to IX times IW divided by times IY divided by IW. So I implemented, just using 4 transistors, a first quadrant multiplier. So remember, currents can only be positive. So this works only in the first quadrant. So if IZ, and then I have here IX, it will be some gain, which will depend on IW divided by, IY divided by IW. Is this clear to everyone? I'm just rewriting the equations of the subthreshold transistors. That would be Vy minus Vw.
Just to be clear, in that case, IX was equal to IZ and IW was equal to IY, and that's why we got that product rule that you did below.
So in this case, IX is completely independent from IY, and IZ is IX times IY divided by IW. So this is not the current conveyor. This is using the current conveyor as a building block, but it's a current multiplier. So if we were to measure this current, the current coming here, this current is equal to Ix. So if we were to call this current Iz, like it was in the current conveyor, Iz prime, this would be equal to Ix. But in reality, we made a bit more complicated circuit and added complexity. So Iz is this one here. So the only thing to keep in mind, so whenever you have a circuit like this, all you have to do is to write, you assume everything is in saturation for simplicity. You write down the equations of the devices, which are these. And then you could basically apply Kirchhoff's current law, write all these equations, and then painfully go through the analysis and write and solve everything until the exponentials simplify out. Or you could say, oh, I remember there is this translinear principle, and so if I notice that all of these VGSs sum to 0, I forget about all the exponentials. I just apply this principle and say that the product of the currents is equal to 1. And so it really quickens and simplifies the analysis. But of course, you can write down the equations. You can apply Kirchhoff's current law whenever there is a node. And then you can solve this system of equations and you will get the same result. You will get that Iz is equal to Ix times Iw times Iy divided by Iw. The translinear principle is just a convenient way of simplifying the analysis and getting to the result more quickly.
Professor?
Yes.
In these equations, when we're looking at Ix and Iy, are we multiplying both Vy and Vx and Vy and Vw for kappa?
Great point. So I was cheating and I was going to ask the question, but you anticipated me. First of all, there is, I always normalize by UT. Remember, all of these equations are wrong. They should be always divided by UT. So I'm just out of laziness, I'm assuming that all voltages are normalized to UT. But then there is the kappa. So if we had bipolar transistors, there would be a perfect relationship between the voltage, exponential relationship between the voltage and the current. But in subthreshold, there is always the kappa. So what I told you up to now is actually wrong. This is only true if kappa is equal to 1. If kappa is not equal to 1, this is an approximation. And if you actually use the equations here and take into account the fact that there is a kappa, you will see that you get terms with kappa square and kappa to 1/3. There are it becomes quickly complicated. So it's a very good point. The subthreshold is only an approximation of the bipolar version. If we had bipolars, it would be perfectly correct. But if we have subthreshold, it's an approximation. So it will be a distorted multiplication because of kappa. So that's always something that will get in the way, this kappa term. And if kappa is not 1, it's usually 0.7. Could be 0.8, but it doesn't get higher than that. So it will be something that gets in the way, and it's an approximation. But I will show you other circuits in which this kappa can be reduced or minimized. The effect of kappa can be minimized. It doesn't go away, but at least we can try to deal with it. But in this multiplier circuit, it's exactly true. The output is going to be some distorted version of the multiplication. It will be Ix2, I don't remember, but we can actually do it just by using these equations, and you will get all the kappa terms come in the way.
So
okay, yes.
Okay, kappa is actually, we were kind of cheating. So we work for kappa equal to 1. But kappa is multiplying both the gate voltage and the source voltage.
So we would have kappa Vx, if we really want to do the VGS, the VGS of the first transistor is not Vx, it's kappa Vx. The VGS of the second transistor is kappa Vy minus Vx. So we have to do kappa Vx plus kappa Vy minus Vx. And then of the other one is kappa Vy minus Vw. So it would be minus kappa Vy minus Vw. And finally, of the last transistor is kappa Vw minus kappa Vw. Now, is this equal to 0? It's not. I mean, in the other case, you could see it, Vx and Vx goes away, Vy and Vy goes away, and Vw goes away. So 0 equals to 0. In assuming kappa is equal to 1, it's like that. But in this case, you get that kappa Vy and kappa Vy go away. But then you have Vx that has kappa minus 1 minus Vw that has, I'm confused with all the minuses. This would be plus Vw minus kappa, so it's also kappa minus 1. Yeah, it's correct. So if kappa is equal to 1, we get 0 on both sides, but otherwise we don't. And now if we put this back into the equations, into the exponentials, and we do everything, we will get something similar to this product here, but with some kappa term. It will be Ix to the kappa something.
Okay, now it's clear. Thank you.
Welcome. Yeah, so it's this translinear principle in subthreshold. It's useful to get an intuition of what's going on, but it does not allow you to have a precise output of what's going on. You always have to keep in mind that there's this kappa that gets in the way. But let's move on. It's 3 o'clock. Let's skip the break because we started like a few minutes late. Let's just skip. I really want to get onto the winner take all. But before I have these other circuits, I want to show you. Maybe I just draw it again. The next one in the slides, in the handouts, I don't know if you have them handy with you. How can I? Okay, here is the current conveyor used as a current mirror. So if we again draw the current conveyor, remember the current conveyor is this circuit here, in which we have an input current. Then we have a bias current here. This was IY. This is Z. This is IX. This is the current conveyor. And now we could just extend the current conveyor and just copy it as many times as we want. So this is a way to copy currents. So again, if we have, remember, if we have this VGS here, it's the same VGS here. So whatever current is flowing through this transistor will be the same current flowing through this transistor and the same current flowing through this transistor and so on. So the normal way of doing a current mirror is just to take the VGS flowing through the first transistor and make it equal to the VGS flowing through the second, the third, and so on. So why would one go through the trouble of adding extra, current sources to implement the same thing that you can do in a simpler way? So let's assume now we're in current mode, remember. So let's assume that our input currents are signals, and our signal is something that's changing over time. And we want to just to copy, this would just be copying. So So you have to imagine I have some remember this is sub-threshold. So I have some picoamps or nanoamps that are, maybe I want to implement a filter or something, but these signals are changing over time. And my output signals should change over time in the same way. But I have, a very long chain. Maybe I have 1,000 neurons or 1,000,000 neurons, and I want to copy the input to all of them. And so if you think of it, when you implement this in silicon, all of these gates and all of these wires going across will actually add a lot of capacitance. It's called parasitic capacitance. It's not explicitly drawn there, but you actually have it because you have lots of gate to source voltages. And so now, because your signal is the current, whenever you try to change your signal because your input is changing over time, you have to load the capacitor and discharge the capacitor. And so the output will actually be a slowed down version or a corrupted version of the input. If your signal has to both represent the signal that you want to process, but also charge and discharge all these capacitors, you're going to be in deep trouble because if you have many of them, it's just going to be washed out. If it's a picoamp currents and you're going at a few even kilohertz, it's just going to be a smooth, washed out thing. So the normal current mirror in that case does not work. If you have a current conveyor, let's see what happens on the top part of the circuit here. So if I apply an input signal that's changing slowly over time, what happens to this voltage? Is this voltage going to be changing? I still have the same capacitors because it's a long wire. I have lots of transistors, so I have lots of capacitors. But the gate voltage here is being actually clamped by the extra transistor of the current conveyor. So you see there is this feedback mechanism with the current conveyor circuit. And because of this feedback mechanism, the extra transistor here that's pushing the same current is clamping the voltage to a constant value, or as soon as we try to change it, the fact that we have a bias current Ix will charge up and discharge the capacitor through Ix. So Ix is the one that's actually making sure that all these capacitors are quickly charged and discharged. And Ix can be nanoamps or tens of nanoamps or hundreds of nanoamps. And whenever Iy changes here, that signal can actually be copied very quickly across. So by adding this extra current source and having the current conveyor with this negative feedback, we make sure that we can charge up and discharge these capacitors. We can clamp the voltage and then copy these currents very quickly. So that's this interesting way of using the current conveyor to overcome the problems that you have with the standard current mirrors. I hope that's clear as well. It's all due to the negative feedback of the fact that, if I have a voltage Vx that is the log of Iy, it is also the source of the top transistor that has to have the V, what is this? This is Vy. Vy minus Vx equal to the log of Ix. I hope you realize what's going on. If I change the input current, Vy doesn't change a lot because it's on the drain. What tries to change a lot is Vx. As soon as I try to change Vx, Vy will go up to the same value such that Vy minus Vx is the log of Ix. And so whenever Vx tries to change, the Ix and the negative feedback with this extra transistor here clamps it to the right value. And so that's why we can speed up the copy of the currents from Iy to all the output transistors. Again, it's a nice trick. It's not crucial for the winner take all, but I wanted to show it to you. And we can move on to the next one because it's already 3:15. The next one is the normalizer circuit, which is also a very nice circuit. It's called the Gilbert normalizer, and I'll show it to you. And again, I'll draw it maybe. Let's see, I just clear canvas and draw the Gilbert normalizer circuit. So let's just start again in current mode. We have input currents, so we have I in 1. Then we copy this current to a transistor. And then we have another input current I in 2 that we copy. Now I'll just do it symmetric for symmetry to another transistor. And instead of just having a current mirror like you would if you connected this to ground, where's the undo? I actually connect all of these to a common node, which is then connected to a bias transistor. So this is constant. And now we can analyze what's going on. So the output currents of the normalizer are I out 1 and I out 2. So this is ground again. So first of all, you should realize that in analog circuit design, just making one single change brings you a new building block. It's really easy to invent new circuits, even now after so many years since the 70s, because there are so many possibilities and flexibility. What you should realize is that what you see here is the differential pair. So we've studied that and analyzed it to the end, so that you would imagine what can you do more with the differential pair. Well, just by connecting it to currents and copying the currents in, you get a new building block that is actually extremely useful. But let's go through the circuits. Let's assume all the transistors are in subthreshold, they're in saturation. So let's just look at what happens at the input currents and the output currents. So the I1 is equal to I0 e to the kappa V, this is V1, this is V2, V1 minus VC. Remember, I always forget to, or neglect to divide by UT. I2 is the same. I2 is I0 e to the kappa V2. Sorry, I forgot the minus VC. And then we know that IO1, this is the standard diff pair analysis, plus IO2 is equal to IB. This is the Kirchhoff's current law. So all of the currents going here have to sum up to IB. So now we can solve for the only unknown is VC. We can solve for VC. So we can derive e to the minus VC is equal to I1 over I0 times e to the minus kappa V1 and I0. In the interest of time, I'll skip it. But if we solve for VC, which maybe we can leave as homework, you will quickly realize that I01 is equal to IB times to I1 divided by I1 plus I2. You can formulate the output as a function of the input only in current mode, in currents. The same for IO2. IO2 is IB times I2 divided by I1 plus I2. And it's really algebra. If you just go through these equations and you derive this, in the interest of time, because of I want to get to the winner take all, I won't do it, but you can see it's really easy to calculate. And you get to this solution. And this can be extended to more than 2 nodes. If you redraw it like this, you have one input tab, another input tab.
One question, the formulas you wrote for I1 and I2, is that I1 out and I2 out, or I1 and I2?
Sorry, I didn't understand the question. Could you please repeat?
Yeah, the formulas that you've written for I1 and I2,
Mhm.
are they for I1 and I2 or I1 out and I2 out?
The equations on the top
Yeah.
here, therefore the input I1, so this this current here, this is I1, is this one, is
Okay.
and the output now there is the unknown e to the minus vc, which is here. So if you solve for e to the minus vc using the two equations and you replace it back into I1, you will get a function of I1 as a function of I01, and then you can rewrite I01 as a function of I1.
How can you know then that from V1 to VC is going to be the same drop from V1 to ground that gives you I1, that mirrors it to I01?
That's the whole point, that the drop from V1 to ground is different from the drop from V1 to VC. Otherwise, I01 would be identical to I1, but it's not. I01 is a scaled version of I1. It's multiplied by IB, and then normalized by the sum of the two I1 and I2. They are different. The drop from V1 to VC is different from the drop of V1 to ground.
But then that one is I1 or I01? Like, as it is considering VC, is it I1?
This is, yeah, the one circled here. This is I1. It's really I1. It's the gate voltage. Oh, sorry, you're right.
Yeah.
It's a mistake. You're right. This is I01. Sorry.
Okay.
I made a big mistake. This is I01 and this is I02. And then we have to write I1 is e to the kappa VC. Sorry, you're right. So this, then you could replace. Let me redo it because it was a big mistake of mine. Okay, ignore everything I said so far. But thanks for noticing it. So I01 is equal to I0 e to the kappa V1 minus VC. And this is equal to I1 minus I0 e to the kappa, times I0 e to the minus VC. Okay, now please correct me if I'm wrong. Is this correct? Does this make sense to you?
Yes, now it does.
Okay, then we can write I02 is the same, I2, I0 e to the minus VC, and then we know that I1 plus I2 is equal to IB. Now we can put all of these three equations together and we can solve for e to the minus VC. Sorry, it was a big mistake, but now I hope it's clear. In the end, you get the same solution. I01 is equal to IB times I1 divided by the sum of the inputs. In this case, it's I1 plus I2, but if you extend it to multiple inputs, you can, where you have this VB, if you have 10 inputs, this applies for I01, I02, I03. So in general, I, whichever tab is IB times I divided by the sum of the currents. That's why it's called the normalizer, because you're always scaling by IB and you normalize by the sum of all the other currents. Now you can imagine this is an extremely useful function, because it's always good to be able to normalize. Suppose you have inputs coming from a silicon retina, inputs coming from a silicon cochlea. You want to compare the two, see which one is more interesting. It's always good to scale everything in the way that they are comparable, and then you can do operations on them. So again, this is from Barry Gilbert, but he invented it for bipolars, but we can do it with subthreshold transistors. In this case, we did take into account the kappa, and there is no problem with the kappa. So in this case, we didn't use the translinear principle. We just did everything, you know, using the equations. And you actually caught me, you even found a mistake. But this last slide here is the correct one. So it's really a pure normalizer circuit. It's really helpful. If it's clear, I can move on to the next. Yeah, it's.
Could you answer the question in the chat? Sorry.
Sorry. Wait, isn't IB? Yes, you're right. IO. That's now it's correct. Yeah, you're right. Sorry, also there I was going too quickly.
I have one last question about these equations.
Yes.
When you describe IO1 as I0 times e to the kappa V1 minus VC is equal to I1 times I0 e kappa e minus VC. Shouldn't it just be e minus VC? Because I1 is I0 times e to the kappa V1.
You might be right also there. I think you are. It's I0 to the kappa V1 because times e to the minus VC. Yes, so it's times e to the minus VC.
Thanks.
Yeah, thanks. Okay, so after all of these corrections, now it should be correct. I trust that you can actually solve it yourself. I was just going quickly, but it's yeah, it's good that you're catching all of these mistakes. But as I said, we didn't make any assumptions for kappa. If you remember to normalize by UT, everything should be okay. And in the end, the nice thing about these current mode circuits is that the output current, you can express it as a function of the input current. And you can even scale it by IB. Okay, if no more, I hope you corrected everything. There isn't any other place where I could make mistakes. So I think we can move on to the next one, which is the winner-take-all finally. Now, winner-take-all networks are extremely useful circuits. First of all, if you look at the brain, so in neuromorphic, one thing is also to compare to what's going on in the brain. There is this idea that in the cortex, there is a canonical microcircuit, like a basic building block, that as soon as evolution found it, it started replicating and replicating. If you look at evolutionary timescales, at the time in which the neocortex appeared, it quickly grew. The size of the brain in mammals, in non-human primates, quickly grew tremendously in evolutionary timescales, like exponentially. Again, I don't know if it's exponential or not, but it was very, very quick. So the idea is that there is this basic building block that nature found that allowed these primates to excel and survive. And then it then was being used everywhere in the cortex, in the visual cortex, in the auditory cortex, in the olfactory cortex, in the somatosensory. And from anatomy, and also from the work that was done, that is being still done at the Institute of Neuroinformatics, it's been shown that there are these motifs that are found in all these cortices that are being replicated all over. So both from evolution, from anatomy, from physiology, there is a lot of evidence pointing to the fact that there is a basic building block that is very useful for doing computation in the cortex. And the studies of Rodney Douglas, Kevin Martin, but also many other neuroscientists around the world point to the idea that this basic building block is a winner-take-all, or actually can take the role of winner-take-all. Maybe if you change the parameters, it can also do other functions like normalization, but it can also do winner-take-all just by changing the parameters of the network. And so it's more like a soft winner-take-all. If you have many input signals coming in, you could select some signals if they are slightly higher. For example, you're at a cocktail party, you hear your name being pronounced by someone, you decide to amplify the filters that, or the input signals that correspond to the pitch or the tone of the voice that you heard, and you suppress all the others. So your signal that gets amplified, and you suppress that, and those inputs win, and all the others inputs lose. So in this sense, this is a winner-take-all circuit, and it can be adaptively adjusted so that, you know, when you pay attention to something, you enhance those inputs and you suppress the others. First, you need to normalize everything, and then, which is what we can do with the Gilbert normalizer. But then you need also to have this gain, or selective gain, selective amplification. And as I said, there are many studies that point to neural circuits that can do that, but we can also do it with analog circuits. And if you assume that one transistor is like the activation function of a neuron, you can also make analogies to neural circuits. So this is just to give you the background that this idea of using winner-take-all networks can be very useful in neural computation. It can also be very useful just in analog signal processing. And I wanted to show you now the circuit that was invented by John Lazzaro, Carver Mead in the early 90s, and which is, it is a canonical microcircuit. If you look at whatever chips have been produced throughout 30 years, it's basically everywhere. Every chip that has been done at some stage or another has this building block inside. So from the neuromorphic engineering point of view, it's really a canonical circuit, like you would have one in Cortex. And let me just show it to you. I can also point you in the material in OLAT to papers that talk about the neural aspects if you're interested in neural computation. But here we will just focus on the analog circuits of that. Let me clear the canvas again and start drawing the circuits. First of all, the function of the circuit is something that if you have different signals that can be noisy, the output of the winner-take-all circuit is supposed to suppress all the noise and amplify the signal, or amplify the strongest. So that's what we want to design. We want to design a circuit that if it's receiving many inputs on many taps, like we had with the Gilbert normalizer, it would then selectively amplify with a gain higher than 1, the stronger inputs, and selectively suppress with a gain, or amplify with a gain less than 1, the weaker inputs. Now, how do we do that with analog circuits? Well, you can imagine it's going to have to deal with current conveyors and Gilbert multipliers. So let's start again with the classical current conveyor. This is, as I said, it's the building block. And if you remember, when we had the Gilbert normalizer, I did it symmetrically. So let's see if I can manage to do it symmetrically even now. But it applies to multiple taps. So now we're just looking at 2 taps, but you can imagine later I will show you this can be extended to multiple. So again, we have an input I, let me call it I in 1 so I don't get confused. And this is IO1. And here we have I in 2 and IO2. And now this is also connected to ground, and all of these nodes here are connected to a common node. If we have more taps, it would just go on to some IB current. So it's essentially what we have seen already, except that we get current that is going directly into the current conveyor input. And now we have to see what's happening. We just analyze the circuit, what's going on with the outputs as a function of the input. So again, remember current mode, we assume the signals are currents, and we look at what is the output versus the input. Now, this is a perfectly symmetric circuit. So we will do the analysis for 3 cases. The case in which the input on one node is equal to the input on the other node, the case in which the 2 inputs differ a lot, and then the case in which the inputs are slightly different. We just have a small signal delta. So you can imagine we can easily get away with the case in which the two inputs are the same. What happens, this would be a common node voltage VC. If the IE, whoops, I don't know how that came about. Let me take it away. I in 1 is equal to I in 2. What happens to the outputs? Can anybody guess?
IB over 2?
Sorry?
IB over 2?
Yes, they're equal, and because of Kirchhoff's current law that the sum has to be equal to IB, they're both equal. It's assuming all transistors are identical. Exactly. So that's the easy case. So now let's look at the case in which I1 is much larger than I in 2. So we have these two nodes. Remember, if I force an input current through M1, what's going to happen to the gate to source voltage? It's going to be the log of that current. So VC will just go up to a high value. Now, for this analysis, it's useful to remember that the current through a MOSFET, if it's in the ohmic region, is equal to the forward component versus minus the reverse component. The forward component, if you remember, is I0 e to the kappa Vg minus Vs, and the reverse component is I0 e to the kappa Vg minus Vd. So when we are in the ohmic region, the forward and the reverse components are comparable, and you have to take into account both of them. Now let's assume I1 is a big current and M1 is in saturation. So in that case, the VC just is dominating, the forward component is dominating. And so VC just goes to the log of I1. We want to see what is happening now to the other branch on IO2. So let's just make this M2 and then this M3 and M4. Okay, so let's look at what's happening with M2. M2 sees a very large gate to source voltage. In fact, it sees the same gate to source voltage of M1, which means that M2, if we were only looking at the gate to source voltage, would be trying to sink I in 1. But on the other hand, M2 can only sink I in 2, which is much smaller. So what other handles are there? In which other way can M2 sink a small current, given the fact that it has a high gate to source voltage? It has a very large forward component of the current, but the total current is small. So how can we make everything, satisfy both constraints? That on one hand, VC has to be large because it sees I1 on the left, but on M2, given that VC is large, we have a small current. So how can that transistor cope with this fact that it has a large gate to source voltage, but it can only sink a very small current, I in 2? Yes, it is in the linear region. Great. It is in the linear region. So what does it mean? So I'm writing now the drain to source voltage. No, we know the gate to the source voltage is ground. So the gate voltage is VC. The drain voltage of M2 is VO2. I wrote it as the output voltage of the second tap. So what's if it's in the linear region, where should VO2 be? Remember, in subthreshold, yes, it has to be at least less than 4 UT. So it has to be less than 100 millivolts. So VO2 has to be less than 4 UT. Okay, so that's how we satisfy this constraint. M2 sees a large VGS. It has a very large forward current, but the total current is small. So the only way for that to be satisfied is to have a very large reverse current. So they cancel each other out. The reverse current is given by VO2, the VC minus VO2. And in other terms, we have to be in the ohmic region, which means that VO2 has to be less than 4 UT. Okay, now let's look at M3 and M4. We know, you told me before, that the sum of the two currents, IO1 plus IO2, has to be equal to IB. But M4 has VO2, which is less than 4 UT. It has a gate voltage, which is less than 4 UT, and a source voltage, which is equal to VC, which is quite large because it's the log of a large current, the log of I in 1. So what is essentially M4 is completely switched off. The gate to source voltage actually could even be negative. So what's the outcome of that? What is IO1 and IO2?
So is this assuming that like this is the extreme in which IO2 is IO1 takes all of IB?
Yes, yeah, it's exactly that, because it's not extreme as long as you have, you know, I in 1 is sufficiently larger than I in 2, then VO2 will go in the ohmic, so M2 will go in the ohmic region, VO2 will drop below 100 millivolts, M4 will switch off, and then M3 will turn completely, will have to basically absorb all of IB. So IO1 is going to be equal to IB, and then IO2 is going to be equal to essentially 0, or it's never 0, it's always the leakage current, the dark current, I0.
I guess my question there was more like, if we see this circuit or the winner takes all circuit, do we always expect, let's call one of the branches to like be working properly in saturation, and for the rest of the branches to not be working at all well into saturation?
That's going to be the case when you have sufficiently large differences in the currents. Now, this sufficiently large is exactly the third point that I said we would analyze when we have small signals. What happens when more or less they're very similar, like you have a bump, a Gaussian bump, and you have, you know, around the center of the bump, you have similar currents. What happens if you have small differences? So, but first I wanted to be clear what happens if you have large differences. It's also an easy case, but you have to, it's good if you understand what's going on. It's that you bring transistors in and out of saturation, and because you do that, then the winner absorbs all of IB, and the losers have basically zero current. So that's why it's called a winner take all circuit, because as the one that receives the input, which is sufficiently larger than all the other inputs, takes all of the bias current, and all the others are switched off. So if you look at current mode, the output is going to be IB for the winner and 0 or I0 for the losers. And if you have a condition in which all the inputs are perfectly identical, then the output is just IB divided by the number of taps. So if it's, in our case, it's 2, it's IB half. But if you had 4, 5, 6, 10 nodes, it would be divided by 10 or so. Now, in reality, in analog, you have mismatch, you have device mismatch. So it's always very difficult to have exactly the same input currents, exactly the same transistor properties. So there's going to be conditions in which you have similar currents, but they're slightly different. And that's the one we want to analyze now. So let me just delete here.
Sorry, one question. Why
Yes.
why O2 equals to I0 and not equals to 0?
It should be 0 in principle, but you know, there's in transistors, whenever you have I0 e to the kappa VG, if this is ground, if VG is 0, if you put 0 here, you get a 1 e to the kappa 0, it is equal to 1. So the output current with the smallest voltage that you can have is always going to be I0. It's never going to go below I0.
Oh, okay.
But in this case, didn't we have a VG that was like negative VGS?
VGS is could also be negative. So you could actually have currents that are smaller than I0. So you could have fractions of I0. Yeah. So that's why it's approximate, but it really depends on the exact numbers that we put. But for this ballpark analysis, probably if depending on I in one, if I in one is sufficiently large, VC will just go above VO2, and so that M4 will have a negative VGS, which will then produce a fraction of I0, maybe I0 halves or I0 tenths, but it still will never be able to be zero. It's details. It's fine in the exam if you say zero, but you should realize it's very hard to get zero electrons to flow through transistor channels. So finally, the last condition is what happens if we have similar currents and we only apply one small change to the other. Sorry, there is another question in the chat. How much larger does I in one? That's okay. That's exactly what we're getting into now. How much larger does I in one have to be compared to I in two to ensure this condition? So that's this analysis here. So let me rewrite this so that question can be expressed in what happens if I in one is equal to I in two plus some small change, some delta I. So, and that's how much does delta I have to be, or what happens when we have small changes? And when do we get to this completely switching on and off, and what happens when we are not in that region? We know that if they were identical, it would be they both have the same output, IB half, but now they're not identical, they're slightly different. And so for that to analyze this condition, we have to think we are operating in the small signal regime also for not only for the M2, but also for M4. Before, we said that M2 would go in the ohmic region, and we managed to solve the circuit just by leaving M1, M3, and M4 in saturation. But for this condition, we have to consider also M3 and M4 in the ohmic region. Let's see what happens. Actually, sorry, this is not true. What I meant to say is for this condition to be analyzed, excuse me, it was a mistake. We have to take into account the early effect of the transistors, not the saturation region. So if we take into account the early effect of the transistors, then we can analyze this condition. And if you remember, the early effect is given by, when we take that into account, if we have a drain current of a transistor with a fixed gate voltage, then that would result in some saturation current. It's not writing anymore. Oh. Sorry. If we take into account the early voltage, that would result in some saturation current. I have to plug my power supply in. I hope that's the problem. There's a power supply here. Sorry about this. In this third condition where we have these two taps, we have I in one, I out one, I in two, I out two. And now the currents are slightly different. And again, we have to use the early effect to be able to analyze this. And remember, if we have the early effect, the output current of a transistor is equal to the saturation current times 1 plus VD over VE, VDS over VE. And assuming S is ground, is VD over VE. So that's the quick summary of how to take into account the early effect. But then if we look at the input transistors M1 and M2, and we replace this equation with I in one and I in two, and one is I in one plus delta, then we get the voltages, right? VD2 is equal to VD1 minus this early voltage part. So that's basically how to understand what's going on in the small signal. If you do the early effect, as soon as you start increasing one current a bit larger than the other current, then the drain voltage, because of the early effect, will start to rise on the transistor that has the larger current. So that's how to basically, you have these two transistors, M1 and M2. They have essentially the same gate voltage, but they have to provide different currents. The only way for these two to satisfy this constraint is to change the drain voltage. And that's happening because of the early effect. So the longer these transistors, the larger the swing will be, because the early effect depends on the length of the transistors. So you have a small signal gain that is dependent on the early voltage. And as soon as you have small differences, the drain of the transistor with the larger current will be going higher than the drain of the other one. Now let's assume I in 1 is the one that is the higher. So the drain of M1 will go higher, but that happens to be also the gate of M3, which is the output transistor of the first tap. So if the gate of M3 goes up and the higher than the gate of M4, then the I out 1 will go higher because the sum has to be equal to IB, but the gate of one is higher than the gate of the other. So now we're in this region in which small differences are amplified by the early voltage. So it's a high gain circuit. And then the output current is exponentially modulated by this high gain voltage. So you can see it's an extremely high gain circuit, because as soon as you have a small difference, you already have the gain of the early voltage that changes the drain voltage. And then the exponential of that is the output current. And that has to be equal to IB. So you have a very, very small region of delta V or delta I in which you can actually see this happening, because it's an extremely high gain circuit. But in the class, you will be able to actually measure this. And that will tell you that that was the question: how much larger does I in 1 have to be compared to I in 2 to go into this domain where you're out of the gain term and one is definitely always winning and the other is always losing. But in practice, it's going to be a very difficult experiment, because it's extremely sensitive to small changes, and you will be measuring these small changes. So I hope this is clear. We went through basically the three conditions. The input is equal to, two inputs are equal, then the output is equal to IB half. If one input is larger than the other, it's easy because one transistor goes into saturation, the other one doesn't. And then all of the IB goes into the non-saturated one. And then if you have small signals, you have to use the early voltage to see what's going on. You have to take into account the fact that there is an early voltage effect, and that will tell you what's happening. You can actually observe what's happening by looking at this, taking into account that there is this early voltage in the transistors. So this is basically the winner take all. This is a hard winner take all, because it's not like the picture I drew where you have bumps and the highest bump wins and the smaller bumps lose. This is just the single input wins and all the others lose. But we can extend this circuit, bringing into finally closing the loop with how we started the lecture with resistive networks. And if we use diffuser networks, we can now create bumps. If we smooth input currents, we can have winner-take-all circuits that act as selective amplifiers for a population of inputs, a bump of inputs, and not a single pixel input. If there are no questions up to now, I'll go on to the next slides to show you how to extend this to this more biologically similar circuit where you can have bumps coming in.
Excuse me, I don't quite understood. Why would we want to get bumps instead of the signal?
So there are many cases in which signals you're trying to process signals that come from sensory inputs, which are smooth in space just by the nature of the input. For example, if you have tactile sensors and you're trying to understand where your finger is touching on a touchpad, that is, it's not a single pixel moving, it's a bump, and you want to calculate the center of mass. So it's useful to have circuits that can actually calculate the center of mass. If you have a blurred camera, you don't have a single sharp pixel that's the highest of all the other pixels. It's a region of pixels. So there are conditions in which you want to be able to process bumps and not, or smooth inputs and not single pixels. And that's why it's useful. In addition, if you're smoothing the inputs, you can compensate for device mismatch effects. As I told you, these are all analog transistors. So you cannot assume that all the input transistors, M1, M2, and all the others are identical. They will have different properties, and so that will bring noise. And if you smooth the noise away, you can still cope with the signal processing. If you don't, it might be that your signal is lower than noise and the output that you get is actually the wrong output because of the device mismatch effects.
Okay, thank you.
Here, sorry, this is a slide showing you current mode and voltage mode measurements on an old class chip. This was before we had the printed circuit board that you're using. You will see slightly different data, but overall, you should see that there is a very small region of inputs. Sorry, let me go back once. You see these ideal input current sources that are providing input currents into the winner take all. They're actually PFETs that are controlled with the gate to source voltage. And the gate to source voltage of these inputs is changed by a few millivolts, like 1 or 2 millivolts. And that will give you the change in the output. That's why I was saying it's going to be a very difficult experiment that you have to do, because you have to find this 1, 2 millivolt, in this case, it's a 4 millivolt range that allows you to see the region in which the loser becomes the winner and the winner becomes the loser, in which they switch. But let's go on to this smoothing part, and I'll just skip through all of these and just go on here. Okay, so this is now the final, yeah, we only have 3 minutes, but it's the last slide. It's the final schematics of the winner take all that has the smoothing and also local inhibition and hysteretic. So your input currents are the same. Your current conveyor is still M1 and M2. It's the same. The global node voltage is the one that has VC, that's set with IB. But in addition, you have some extra circuits. You have laterally connected transistors, V in and Vx. These basically smooth the input laterally and the output laterally. So you can, if you turn them on, you can turn on the space constant. For example, M9 and M1 implement the diffuser network that we analyzed in the very first slides, and you can smooth the input. That will basically, the input going into M1 will be the smooth version of IN. And the same for M8 and M2. You can smooth the output currents. So the output currents will diffuse laterally and will be smoothed. You can measure the smooth input current through this diode current mirror here. So in I-all, you can actually see the input plus the contribution from the neighbors. So this is also useful to have this extra current mirror here. And finally, the last trick is to have this positive feedback here. So suppose this is the winner and you provide an input current. The output current will be equal to the bias. And then what you're doing is you're copying the input current, sorry, the bias current back into the input. So after this becomes the winner, the total input current will be IN plus IB. So once you win not only by a margin that is given by I in being greater than all the other inputs, but all of a sudden you get this plus IB. So this adds you this extra boost. Now, if you want to lose, you should not, you cannot go down becoming less than I in, just a lightly less. You have to become less than I in minus IB to become the loser. And this gives you a hysteretic window, and you will be measuring this hysteresis property in the lab. So it's a another very useful feature. It's like a way that once you win, the noise will not get you away from this winning region. If there is some noise in the input, you don't switch with a high gain across due to noise, but you have a margin that's given by IB that allows you to stay the winner even though your input might be noisy. And finally, yes, the output is just that thing that allows you to measure the output current. And again, this can be a two transistor or a 2-node winner take all, a 5-node, a 10-node, a 1,000-node. You can just scale this up to as many units as you can put on chip. Finally, just before we close, we did all of this analysis for steady state. So we assumed that the input is constant. And all of the equations we used are looking at steady state. But of course, if you have a sine wave or a step or something that changes over time, we can do a small signal analysis, adding capacitors to wherever you have parasitic capacitance, and see when is this stable or not. And we will find conditions for that to be the case on the bias current, the input current, and the various parameters. But yeah, there is no time here. There's already a lot of interesting things that can be done in steady state. So in the class, you will just be doing steady state experiments. Yeah, I think that was the last slide. And yeah, we're just in time. Sorry for all the mess I made with the various Zoom things, and thanks for correcting all the mistakes I oversee. It's really good that you're paying attention. But I hope at least I gave you this feeling of what current mode circuits are, that, you know, if you work with input currents and output currents, you have current mode. Remember, in subthreshold, these input currents can go from 10 to the minus 14 to 10 to the minus 9. So you have a huge dynamic range, even though the power supply is, you know, less than 1 volt. You still have this huge dynamic range that you can use to do computation. So current mode is very useful, especially when you have a small voltage swing in the power supply. And we will see next week how to actually implement filters, temporal filters using current mode circuits. So these are useful not only for steady state, but you will see we can actually do very interesting circuits using the translinear principle and all the other things we did, also for time changing signals, like, you know, first order low pass filters. Yeah, I think that's all. Are there any questions on this last very, very quick run through the hysteretic winner take all?
I have a question.
Mm-hmm.
I guess, I mean, I guess you didn't touch on it, or maybe you did when you talked about the early effect, but what, for example, in this last one, what determines the threshold or the hysteresis window, like, of that each current has to eventually be the winner takes all? Like, what in the circuit determines what it needs to be the win threshold?
So in the simple one, you have to be larger than some delta that really depends on the early voltage. So as I said, it's just, you know, 2 millivolts are enough to make it switch completely from losing to winning. If we put the hysteretic part on, let's assume that, you know, you start everything up and someone becomes the winner because it has a higher input. Now, if someone else is winning, that circuit was winning because it had a current which was larger than this current, but then it is now winning by a factor of also IB. So if you want to take over, you have to provide an input current which is larger than the winner current plus IB. That allows you to overcome this hysteresis problem. And if you want to lose, it's the same thing. If you want to become the loser, you have to go less than the second highest current minus IB, because IB is basically this hysteretic current that comes back in, assuming that the gain is equal to VDD. you can decrease this IB by decreasing V gain just by a few millivolts. Again, this is very, very sensitive. And if you put V gain is equal to VDD minus 1 millivolt, you decrease the hysteretic window.
So we can tune it kind of with the IB.
Yeah, and it will depend on the amplitude of IB, of course. The hysteretic window, if VDD is equal to V gain, will be IB. If IB is greater than all of the input currents, there's no way of changing the winner take all output. Once it chooses something, if IB is too strong, and there is no way of going away from that, it will just be stuck. But if IB is smaller or comparable to the input currents, then the input that will be greater than the winner plus IB will make it switch. So you can tune it by changing IB, or you can tune it by fixing IB and changing V gain.
Thank you.
Yeah, welcome. Okay, if there are no more questions, then I guess we can close here. All right, so I'll stop sharing if I figure how to do that. Yeah. And yeah, thank you for your attention. And just feel free to write to me, send me email or whatever you want if you have questions at any time. And worst case, I see you next week. Okay, bye-bye then.